All right, welcome everybody to week 2, day 1. I'm out sick, maybe with COVID, maybe not. We're going to do a top 20 hits of ARM32 today. Top 32 hits? I don't know. We're going to go over like all of ARM32 assembly programming today. Let's just try and knock it out as much as we can. It's a big topic. I'm going to pause occasionally for you to write code and compile it. So I'd like all of you to log in on the server. If you're a random internet person at home, get a Raspberry Pi, or you can install like QEMU or something like that, QEMU, to install like an ARM32 emulator. So let's take it from the top. The most basic thing, there's a couple different ways of doing ARM programming. We're using the GNU compiler suite to compile our code, which means our program starts with main, not with start. Start is technically the beginning point in a program, and we're starting at a kind of a higher level today. We're starting with main instead, and so we're basically just going to build our projects just like we do with C++. So here we got an assembly programming program, and we're just going to GCC the program. You notice that assembly files end in .s. That is the extension for assembly files. And if I run it, you can see nothing happens because this program simply returns a number back to the operating system. So I was returning 420. You might notice that the number that came out was 164. 164 plus 256 is, of course, 420, if I'm doing the math right. Yeah, okay. So you can only return a number from 0 to 255 with this method. So if we return 20 instead and run it, echo $? Gives you the error code for the previous command. Now if I do that again, I get 0. Why? Because the previous command was echo now, right? And so if I were to like compile the program and then echo the result code, there was no error, right? Because that means the program compiled successfully. Now, if I were to break this and make bad code and try compiling it, I get a error. I get an assembler error, right? And actually, it's kind of nice. Like, it's not as bad as a linker error. Right? It tells me anytime you have a constant number in assembly, it needs to be prefaced with a pound sign. And it tells you that. That's really nice. And if I were to echo the error code, you can see that GCC returned 1 this time. Okay, so let's go through the top to bottom. Let's do ARM32. So every program that you write in assembly is going to start with this global main and main. And there's actually, if you wanted to call any functions, there's actually a little bit more boilerplate that you're going to do. We talked about that last Thursday, but today is just going to be a top to bottom. Let's go over ARM32. So we're just going to start with this. There's actually a little bit more boilerplate that you need. So let's explain this. So when you compile with GCC, it's looking for a function called main. That's your entry point into the program. Technically, the entry point into a program is _start. _start, though, calls main. And it does things like set up the I/O buffers and things like that. So things like printf work and things like that. So you can write something without GCC using something called AS. But if you do that, 1_main, strange. It didn't make an a.out. All right, ls-l a.out. It did, but it's not executable. So chmod, everybody may execute. A.out, run, exec format error, binary file not executable. It's a pain because there's different command line parameters you have to pass to it to make everything work right. And I don't remember them because I just use GCC to compile my code. GCC is a suite of programs. It's a collection of programs. That's why it's called the GNU Compiler Collection. And it sits on top of programs like AS, which is the assembler, LD, the linker. There's the preprocessor, whose name I always forget. There's the actual compiler itself. There's a bunch of tools that all work together in harmony kind of under the hood to make your program. And like we talked about last time, when you make a program like then main.cc, you got this program. You can actually stop it. Step 1 is the preprocessor. Step 2 is the compiler. Step 3 is the assembler. Step 4 is the linker. And when you run it, there's something called the loader. So, so you can actually stop the process anywhere along the way. So if you compile your code with G++, put that back up top, -E, what that's going to do, it's actually going to just show you the result of the preprocessor. So if you want to see what your code looks like after the preprocessor is run, G++-E will do so. If you write that to a file, we write it to a file called a .I file, which is a intermediate file. I don't know what it stands for actually, but that means it's been preprocessed already. And then if you wanted to, you could G++ main.I, and it works, you know. So the compiler actually looks at the suffix of a file to tell you what kind of file it is, right? A .c file, if it's like main.c, that's C programming language. If it's a .s file, it's assembly. .cc, it's C++, 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 C++. There's like a bunch of different extensions, all meaning C++. And yeah, and then main.o, it would be an object file, so that's after the assembler runs. So step 1 is the preprocessor, step 2 is the compiler. If you want to just compile it and stop there, you do that, and then that generates a that's going to do the compiler and the assembler, and it generates a .o file. If you want to stop with the assembler step, main.cc, you do that, and then it generates a assembly file. So you can kind of stop after every step, right? And so you can stop after the preprocessor, after the compiler. Yeah, I did these out of order. Sorry. So that's the like stopping after the preprocessor, stopping after the compiler, stopping after the assembler, right? And then after the linker runs G++ main.o. Remember, the compiler can take any extension. It'll actually figure out what step needs to run. Then it generates for you an a.out. And when you run it, something called the loader runs, and it loads it into memory. When you make a program, we're going to have a whole lecture on this, but programs oftentimes link against what are called dynamic libraries, and so when you run the program, it's actually got to find those on disk and pull them into memory, and that's the last step. And that's normally invisible to you, except apparently if you're using address sanitizer on here, -f sanitize equals address main.cc, because it's not configured correctly. So when you try running it, you get a problem with the loader. So so if you want to use address sanitizer in this class, until I figure out that problem, use Clang instead of G++, and it'll work fine. Okay, so address sanitizer, for whatever reason, on the server runs just fine on Clang, but it might just be because we have an old version of G++. I don't know. Raspberry Pis are not as up-to-date software-wise than, you know, mainline things. Okay, so let's do assembly. Seg faulty on test 11, stack overflow issues. We'll deal with that later. We're talking assembly today. So this is where we were last time. So this says there's a function. .global is a directive, meaning this is a function that can be called from elsewhere. Anytime you have a function that wants to be sort of exposed to the rest of the world, use .global. If you put something in here that's not, you know, whatever, Jojo or whatever, G++, _main, then you see main is right here as a capital T, and Jojo is a lowercase t. So They're if you ever want to make a, and don't worry, it's text segment, but don't worry about it what it means. The point is that this is like a function, okay, whereas this is just a label that you can jump to, which we'll talk about in a little bit. All right, so basics of assembly. Move will put a value, it'll copy a value into a value, and you can also move from one register to another. What's a register? A register is the hardware equivalent of a variable. So if you move from register 1 into register 0, what value does register 1 have? I don't know. It's not set anywhere. So it's unclear what value it'll have. But if we did something like this, then R1 will be 20 afterwards. Right? So this command here sets R0 to be 20, just like in C++, x equals 20. Let's say R0 is x for whatever reason. I typically name my registers just so that I can keep track of them in my head. So this puts 20 into register 0, and then it moves the value of register 0 into register 1, which I don't know why we're doing that, but it would be 20 as well. Here, let's make this 42 because that's what it was originally, right? Okay, and then this is how you can exit from a function. We're going to learn a better way of doing it in a little bit, and yeah, and that there, if you branch to exit, that's another way of exiting, and then this is another way of exiting. This calls a system call. The system call terminates your program, and so we usually just return from main. Like in C++, we usually return from main, but if you want to call exit, you can do so as well. That's kind of the preferable way of doing it. Okay, so save that, and so there's different arithmetic operations in, do I have more of them in here? Subtract, multiply, divide, yeah, okay. So in assembly, the first command you learn is move. That just sets a register to a value. So this is going to put the value of 10 into register 0. There's 16 registers in ARM32, register 0 through register 15. Never touch register 15 or 14 or probably 13. And register 0 is always used for return values. And we'll talk more about preserving the registers between function calls. In general, the general purpose registers you use are registers 4 through 11 for doing your computations. Registers 0 through 3 are called scratch registers. They're not preserved if you do a function call. Yeah, okay. So how do you add two values together? You pass in a register and a register, or the third parameter here could be, 42 or whatever. And but this one cannot be. Like this is not valid. This is not valid ARM. In ARM, almost every command, almost every 3-parameter command, like add, subtract, etc., have a flexible third parameter. So that means the third parameter can either be a register or a constant. You guys understand? For all my examples, I have the C++ code up here, and then the assembly equivalent down here. So I'm just arbitrarily calling x to be register 0, y to be register 1, x is equal to x plus y, and then we add 42 to x, and then we return. Any questions so far? So we've learned 2 assembly commands so far, maybe 3 if you can't BXLR. Move sets a value. Add adds two values together. BXLR returns from a function. Sounds straightforward? Okay. And it is. ARM32 is surprisingly easy to learn. All right, so let's move on to subtraction. Yeah, subtraction works just like addition, except it's backwards. So x is equal to x minus 58. Okay. So, yeah. There is also reverse subtract. Reverse subtract is something that one of you was Shahab was asking about, and that is the reason why reverse subtract works is because you can't do this, right? So if you wanted to set R0 to be 58 minus R0, can't do that, right? Because the flexible third parameter, only the third parameter could be a constant. So reverse subtract equals 10. So x is equal to 10 minus x. Okay. This is reverse subtract. Reverse subtract, or you need a constant. The first operand. Okay. Will there ever be a case where you set R0 equal to user input? Yeah, of course. Absolutely. Everything you do in C++, you can do in assembly. Why? Because C++ turns into assembly, right? And so the reason why we're not doing that here is because it's surprisingly hard. So it's actually really difficult. Like if you're not using CN or Cout or scanf or printf, which are the C world equivalents of CN and Cout. How do you do it in assembly? It's week 6. You know, it's actually really, really difficult because there's a system called the operating system, but it just gives you an array of characters. So if somebody types in 420, you don't get 420 from the operating system. You get the character 4 and the character 2 and their character 0. But they might not have typed 420 directly. They could have typed space, 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 420. So now you have to write a program that reads and munges, eats all the leading spaces. Oh, I got a number. Okay, the number is 4. Okay. You read the next character. Oh, it's a 2. So you have to take your old quantity, multiply it by 10, add 2 in. Oh, I got a 0. Take 42, multiply by 10, add a 0 in. Oh, I got a new line. Okay, I'm done. So my final result was 420, and you put that into a register. It's a pain in the ass. Okay. There's no, like, CN. Like, you can't just CN into an integer in assembly. Because the only thing you have to work with is the functionality the operating system gives you. There's no standard library in assembly. So all those nice things, because the CN is part of the standard library. It's not part of the C++ language. CN is part of the C++ standard library. It's a standard way of reading values from the keyboard into a variable. And in C, we have printf, which prints a variable to the screen, and scanf, which reads from the keyboard into a variable. And these functions are massive. These are really, really big. They're like, I don't even know, like 40, 50,000 lines of code to implement. Because they have to not just handle integers, which are reasonably easy as far as these things go, but they have to handle floating point numbers, and there's a lot of weird floating point numbers. Like the rules on floats, we'll have a whole lecture on that. It's weird, you know. And so you got to handle all the possibilities, and it's just I don't want to write it. I want to use the standard library. So checking every character, yeah, and that's just for an integer, Aaron. It's not. It's that doesn't even have, like, I didn't even mention negatives because there could have been a negative 420. And what if it's like a 4, then a negative, then a 20? Then it should return 4. You know, like it's, and trying to write that in assembly, I'd rather use the standard library. And so for this class, whenever you do I/O stuff, you're gonna do the I/O part of things in C++ or C, your choice, usually, and just have those things return values back to your assembly. You're gonna have to do all your coding in assembly, but anytime it's like read from the keyboard, you're gonna call a C function, and the C function is gonna return a value back to you. So yeah. Look into the implementation of printf sometime. It takes an infinite number of parameters. Like it's interesting in a kind of horrifying way. Okay, so multiplication. Special note: mul does not allow a flexible third parameter. Okay, so if you're going to multiply two numbers, multiply it by 42, doesn't work. ARM register expected. You cannot use a constant in the third parameter for multiply. That's an exception to the general rule. The general rule is the third parameter in ARM can either be a register or a constant. Okay, and the reason for that is because mul can run over multiple cycles, and so that intermediate value would have to be stored somewhere through the multiple cycles of running. And maybe, I don't know, or that's just my guess why it is that way. I actually don't know for sure, but that seems reasonable to me. That it would have to be stored in either register or in the instruction. I guess it's in the instruction. I don't know. There's probably some implementation detail that 20 years ago that seemed like a good idea. I don't know. Okay, so you guys understand this code here. A function called main. We're putting 21 into register 1. We're putting 3 into register 2. We're multiplying register 1 and register 2 together and storing the result in register 0. Register 0 is always the return value from a function. When a function returns a value, it's always returned in register 0. But you're like, but wait, what if we're supposed to return a short instead of an int? What if we're supposed to return a char? Doesn't care. ARM has no types. Whatever bits are in the register had better be the right type. Okay. Can't return a long in one register because these registers are 32 bits. If you wanted to return a long, which is 64 bits, you would put half of it into register 0 and half of it into register 1. Then R0 and R1 are both used for the return value. If you ever have to return a 64-bit number, it uses both register 0 and register 1. Okay, good question. All right. And if you want to do a double or a float, we'll have a lecture on floats, like I said, at some future date. All right. A lot of times when you do assembly programming, you just don't use floats. It's actually, you can see here floats are, lecture 13 and 14, right? We're on 4 right now. And why is that? Well, let's say that you get a job as an assembly programmer. What you're going to be programming is probably not World of Warcraft or Call of Duty or something like that, which do use floating point numbers, what fraction of the health bar should be filled up, that kind of stuff. A lot of times you're programming things like this, like remote controls, where they have a little ARM CPU in here that costs $1 or whatever, and they've got a K of RAM, And so you program it in assembly because, C++, just using IO string, like those 40 or 50,000 lines of code, if you guys remember that, This program here is 8K. What does it do? It returns 20. It's 8K. So, if Arduinos have 8K of RAM, like this would explode the Arduino's RAM budget. Just this program that returns a single thing, and that's because we're using G++, which links in the standard library and some other stuff for us. If we were doing this in if we were programming one of these things, we might very well write it in assembly, and our code might literally be 50 or 60 lines of assembly. Some of these things. Some of these things are very simple. You got buttons. You have a thing that says if the button's pushed, then send this signal to the infrared controller, and the infrared controller, does its thing. If any of you guys have played TIS 100 or Shenzhen IO, which I recommend all of you play, TIS 100 and Shenzhen IO are both great programming puzzle games that will teach you the mindset of doing assembly programming. You might write an assembly program and you compile it with AS instead of G++, and you get an executable that's much, much smaller. And then you hard code it onto like a ROM. Like, so it's not even like a program in the traditional, like it has to be loaded from disk and stuff. It's just kind of, there, and every time they hit a button, it runs the assembly, And if you look around the world around you, how many CPUs do you think are in the room that you're in right now? Just out of curiosity. I'll count mine. I count about 23 CPUs in the room around me. One of them is an Intel. No, one, two, three. Three of them are Intel CPUs. The other 20 are ARM. Okay. Yeah. So your mouse, right? Like my mouse is a programmable thing in it. You can have a little LED thing. It's programmable. It's and so a lot of those things, like you don't want like some big thing running on it. RAM's expensive. I mean, it's not, but when you're making a remote control, if you just add $5 to the cost to make it, like that might be make or break for your remote control. A remote control might be $7. And so if you add $5 to it, you're going to lose to the competitors that can use a cheaper part. Right. So, okay. So check out those games. All right, let's take a look at division. So division in ARM. First of all, I should mention there is no division or modulus in ARM32. In other words, there is no division command or mod command. I would typically get students on that on midterms and finals. What does this line of code do? Div, R1, whatever. And they'd be like, it's doing division. No, there is no division. There is no modulus command in base ARM32. ARM has extensions to it and coprocessors and things like that that can do floating point. But by default in your base ARM32 v6 that we're programming in, there's no division or modulus. You have to do Neon or something, yeah. VFP, Neon. There's a variety of extensions to ARM32 that will allow you to do division. By default, there is no such thing as division or modulus. You can, if you look through the textbook, excellent books by Bruce Smith. Highly recommend this. I was on a gaming channel last night about 1 o'clock in the morning, and some experienced student was saying, you should buy the book. So, $20. So you know it's not a real textbook. It's a book for actual people. If it was a textbook, this would be $300. So yeah, Bruce Smith is real. I really love his writing. Very clear, very understandable. Takes you from A to Z, and just explains everything really well. Highly recommend. It's one of those things where like college students will typically like anytime something's optional, like they won't do it, But I kind of feel like it's not a long book. Yeah, maybe it is. It's gotten bigger over the years. It's like 300 pages now. When I first bought it, it was smaller. But he has source code in there for implementing division in assembly, using like shifts and things, logarithms. I don't know. It's all too complicated for my small brain. But it's like 70 or 80 lines of code to do division in assembly by hand. I guess you could do like repeated subtraction, but that seems slower. Like there's some way of doing it with shifting and things that makes it not too bad. Now, that said, I will show you a way to do division, as long as it's a power of 2. So if we have x is 32 and y is 8, 32 divided by 8 is 4, right? So we run this code, g++ 5 div, and we get 4 as a result. So how the hell do we do division if there's no divide command? Well, there is something called shifting in assembly. And that means you take all the bits in a number and you shift them left or you shift them right. And in this case, we're shifting them right. And so in binary, let's say you have the number 1011, which is equal to 8 plus, there's no 4, so it's 8 times 1 plus 4 times 0 plus 2 times 1 plus 1 times 1. So you see that 1, 0, 1, 1. That's how binary digits work, right? This is the 1's digit, that's the 2's digit, that's the 4's digit, that's the 8's digit. So this number here is what? $13. Okay. So let's say we right shift it once. If we right shift 1011 once, it becomes 101. All the digits move right one spot, and zeros fill in. 101 is equal to 4 times 1 plus 2 times 0 plus 1 times 1. Did my explanation of binary confuse you, or did you guys kind of know that already? 8 plus 2 plus 1. It's the 8th digit, so 8 plus 2 plus 1 is 13. And so, sorry, I can add. It's 11. There we go. Maybe that was confusing you. Okay. So, see, I was just seeing if you guys were awake. Right. So if you right shift 11 once, that's like dividing by 2. 11 divided by 2 is 5.5, but we're dealing with integer world, so 11 divided by 2 is 5. Okay. If we right shift it twice, it becomes 10. 10. Okay. So 11 divided by 4 is equal to 2. If you right shift it twice, it's not division by 3, it's division by 4. If you right shift it 3 times, it's division by 8. If you right shift it 4 times, it's division by 16. Every time you shift the digits right once, it's division by 2. So as long as you're doing divisions by 2, or even multiply by 2s, you can do with a shift the other way, right? Then you can actually do division. And shifting is fast, actually. So shifting technically takes no time, actually. So so for example, if we wanted, we could yeah. So you do it like this. So we're moving R0 into R0, which is kind of a waste. We could have moved it into like R1 or whatever. So we're doing basically a no operation here, you know. But we could have been moving it into a different register or whatever. And every time you do an operation, you can do a shift with it. And so you can do a logical shift right, which is moving the bits 3 to the right. So we're taking all the bits and shifting them 3 to the right, and that is the same thing as dividing by 8. 2, 4, 8, 3. Okay. If I wanted to divide by 32, how many bits right should I shift it? If I wanted to divide 32 by 32, what number should I put there? How do I divide by 32 in ARM32 assembly? Five. Very good. McCowan. Very good. Yep. So, yeah, you can do division as long as it's power 2. And then there's tricks to do other things as well that we don't need to worry about right now. You guys understand? Makes sense? Sorry, you right shift it twice. Yeah. LSR is not division, it's just right shifting the bits. So LSR shifts the bit, it's logical shift right. So this is the format for it. You move from R0 into R0, and then you can always do a shift with most commands in ARM assembly, and that will do a you can do a left shift or a right shift on top of the operation here. So this takes R0, shifts it right 3 times, which does division by 8, and then puts the result into R0. That's the format for shifting. LSR is division. It's not division. I mean, it's bit shifting. Like, it's not a divide command. It's just saying take all the bits in this register and move them right 3 digits. And if it's an integer, that's the same thing as dividing by 8, because every time you shift to the right once, it's division by 2. Divide by 2, divide by 2, divide by 2. 8. Make sense, Aaron? This is how you do it in C++, by the way. Not a lot of people know about that. So that is a right shift by 3 in C++. Okay. If you wanted to do multiplication by 8, you can do a logical shift left, like that. And then it would multiply by 8 instead of addition by 8. Aaron, you understand? Decimals get thrown away because they fall off the edge of the world. If you left shift and bits fall off the edge of the world, you overflow. Are these numbers signed or unsigned? I don't know. You tell me. There's no types, and there's just bits. In assembly, everything's just a bit. Okay. Gotta tell me, Aaron, if you understand or not. I see you keep typing, but you're not hitting return. We're about to move on to the next big topic. So, if anyone has any questions about McCowan, I saw you were typing something too. We're just shifting left or right depending on the purpose of the program. Well, if you left shift or right shift if you want to multiply by 2 or divide by 2 or power of 2. No worries. Okay. So that is the basics of like making a program and doing add, subtract, multiply, and shifting. Now we're going to talk about branches. Okay. So here we've got a C++ program. All my examples, I'll push out these examples to you at the end of the day, by the way. I'll do it now. I don't care. So here, all my examples start with the C++ equivalent, so you can see the equivalency between the C++ and the assembly. Yep. So here we've got x equal to 32, y is equal to 20. If x is greater than y, we, I don't know, just do some stuff. We're going to increment x a bunch of times. Otherwise, we decrement x a bunch of times. And what we're doing inside of these branches doesn't matter. The point is, I want to explain to you guys, how do you do a conditional? How do you do an if statement? How do you do a branch? These are all equivalent terms. Okay? You guys ready for this? You guys pumped up? Gregorian? Knight? Vargas? You guys stoked? You excited to learn how to make your assembly programs intelligent? Because remember, if statements are the intelligence of your program. You know? They're the brains. That's where decisions made. All right, let's do this. So, if statements in assembly are kind of interesting, actually. They're kind of interesting. Let me show you how this works. So, so here we got main, right? And we're putting x 32 into x, 20 into y, and here is how you do a comparison between x and y. You might be asking, what comparison is it doing? Is it doing greater than? Is it doing less than? Equals to? Not equals to? Less than or equal to? Or greater than or equal to? And the answer is yes. The answer is yes. It does all 6 comparisons at the same time. So by doing a comparison operation, CMP, compare, pretty much every assembly command, by the way, is 3 letters with very, like BX, I guess, is not. But almost every assembly command is 3 letters. So this is comparing register 1 and register 2. It's doing greater than, and less than, and equal to, and not equal to, and greater than, equal to, and less than or equal to, all at the same time. Okay? You guys grasp this? Your head? In C++, that is now a thing. It's called the spaceship operator because it looks like a TIE fighter, but they couldn't use the copyrighted term, so they call it the spaceship operator. But in C++, this does all 6 comparisons as well. It's a thing now. So, so it's not branching yet. We're about to get to branching on the next line. The B stands for branch. This is just doing a comparison. Okay, so the way that it works in assembly is that you first have to do a comparison of some sort, and CMP is the most common way of doing it, but there's actually other ways of doing comparisons as well. And when a CMP is run, there is a special register that you can't access that holds the results of that comparison. And it holds the results of that comparison until another comparison is done. Okay? So this, you could go all the way down to here, and because you see there's no other comparisons anywhere within the code, the results of this comparison would still be in the register by the time you got all the way down to like here or whatever. Okay? It sets the secret registers, and the register holds, was the result greater than, was it less than, was it equal to, and those are, they could both be set, like it could be both greater than or equal to, right? If you do a greater than or equal to comparison, right? It checks all 3. And so this B command here is how you do a branch. Okay? L1 and L2 can be named anything. I can call this one Bob, it doesn't matter. These are labels. So anytime you have a colon like that, that is a label. It is not an assembly command. It doesn't run anything. It is a way of, like, you can put it like this if you wanted to. It's a way of naming a line of code. Okay. So this line here is named L1. Okay. That label is not a function, it's a label. This is a function. This can be called from C++. This could not. This is used internally only. So when you jump to L1, which we do here, it has to be within the same source code file, basically. Yeah, it's not a global. It's just a name. Just labeling this line of code here is called L1. Okay. And so what we're saying is branch if greater than to L1. So if x is greater than y, jump to L1. Otherwise, branch if less than or equal to, jump to L2. So B by itself, by the way, works. That means branch to L1. When? Always. So if I wrote this code right here, it would always come here, it would do the comparison. The comparison wouldn't matter because the branch would immediately jump to L1. Okay. Another way that people write this is British Airways, branch always, branch always is the equivalent to this. Okay, so what kinds of things can go here? Well, there is branch always. There's branch never. I don't know why you would do that, though. It seems like a waste of lines. I'm not going to tell you. Branch greater than means like branch if greater than, right? Branch if greater than or equal to. Branch if less than. Branch if less than or equal to. Branch if equal. Branch if not equal. So that means like if x equals y, double equals y. You guys get the idea, right? Okay, so this code here says if, and it's based on the results of the previous comparison. Comparison and branch go together like peanut butter and jelly, okay? You can't do a branch without a comparison. You do a comparison first, then you do the branch. Like I said, there's alternate ways of doing comparisons, which we'll learn later. But for now, you do a comparison, and that sets the secret registers. And then when you do a branch of greater than, the branch of greater than instruction checks the secret registers to see if the results of the previous comparison was greater than, and if it was, then it jumps to L1. If it was not, if it was less than or equal to, or I could have written BAL there, right? Branch always, that would be equivalent, right? Because there's only three possibilities: greater than, less than, or equal to, right? And then if it's not greater than, if it's the else statement here, then it will jump to L2, and then it will do the subtractions, right? Oh, yeah, this is actually a good point here. There are usually two parameter versions that are like x minus minus. Yep. So this is like x is equal to x plus 1. This is like x minus equals 1. Okay. You guys see the difference? So if you give two parameters, if you omit the middle one, then it assumes the middle one is the same as the first one. Yeah. You found the forbidden B and V. There are other ones. There's BCS and branch of carry set. So like if you add two numbers together, it'll set the carry bit if it overflows. There's all sorts of other, branches, but these are the main ones. So, you guys understand? And so the code runs, assembly code just runs from the top to the bottom. There's no curly braces or anything like that. They just start at the top and they go down, was 32 greater than 20? Yep, okay. Then it skips over this line. This line of code is not going to run, right? Because it's skipping over it. When you do a branch statement, it jumps to a line of code. So it's immediately going to skip over this one, jump to L1, and then add, and then after we do 10 adds or whatever it is, it branches to done. So that's going to skip over all of this code. None of this code is going to run here. None of that code runs. It skips over it until it gets to done, and then it returns. Okay? So, hail to the chimp, CMP. So, yeah, that's it. And then at the bottom of one of these things, if you want to do a loop, you just branch back upwards instead. All right. So if you want to have an infinite loop, there you go. That's an infinite loop that'll run forever. You guys see that? So gets to the bottom, jumps to the top, keeps going. That's how you do loops, by the way. There's nothing. There's no loops in assembly language. Hail to the chimp. Yeah. Okay. Would a nested if be a branch inside of a branch? Yeah. Yeah. So you could do something like here. You could like compare R0 with 10, and then branch if less than or equal to done. You know, something like that. And if it's not less than, then we'll keep going. Okay. So. Yeah, you can put these kind of wherever, and you have to be careful to structure your code so it doesn't turn into like this giant maze of like this jumps here and then it goes here and it jumps here and it goes here and it jumps here and it goes here and it jumps here and it goes here. It's called spaghetti code because it looks like the flow of control looks like a plate full of spaghetti, right? Mom's spaghetti. So yeah. So if you want a nested if, yeah. So you could like jump to here and then do another comparison. Okay, so the first one was if x is greater than y, and then you come in here and you check to see if z is greater than 10, and jump here. And I keep track of that by, again, I typically put the C++ equivalent in there, like, this is what I'm doing. This is this part of code, you know, the 10 x++s, or, you know, is this, right? So, yeah, it can get complicated. Okay. So here's another one. Yeah. So there's actually two different ways you can do if statements in ARM32 assembly. This is the basic way. You do a comparison, you do a branch. And the branch goes and runs a block of code. And the way that you typically structure it is like this, right? Like if you've got an if and an else, like you've got your if the if runs, a big block of code runs, and an else, and a different block of code runs, and then at the bottom of both of those, they jump to here. You guys see that? So one branch goes and then it jumps to here, right? Other branch runs, jumps to here. So the flow of control looks like this, right? So you have a branch, and then they come back together, right? Does that make sense to you guys? So at the bottom of the if part, the bottom of the else part, they both come back together here. Now technically, if I deleted this, it'd be the same. This actually doesn't do anything, because done's the next line anyway. Right, this is assembly. There's no curly braces. If you deleted this, it would just fall right through to the next line, right? So, you guys see that? Do you guys see why the BAL is not necessary? Because assembly just runs from the top to the bottom. The only time it doesn't is when you get a branch, and then it jumps to a specific line. So this line of code here is saying jump to this line. If we deleted it, it would just continue on its merry way down the text file, and it would run this line anyway. So, are there people awake? I know Aaron's talking, but there's like 20 people in on chat. Okay, all right. So I'm going to pause it here, and I'd like for all of you to write the following code in move main.cc. X equals 10, y is 20, and z equals 30. If x is less than y, x is less than z, else So write this in assembly. Assembly is useful go-tos. C++ is useful go-tos also. We just don't use it because we've got curly braces, right? The curly braces tell us where to go to. Like, well, I mean, these are returning, I guess, but like, you know, normally when you have an if statement, when you finish an if statement, you jump down to the closed curly brace, right, and keep going. It does the go-tos for you, that the flow of control where it jumps to the appropriate thing. Like if you look at assembly that's generated, you see how there's labels all over the place. There's labels all over the place, and these are generated by, you know, the loops and any place that it can jump to or load from. You see how there's just labels everywhere in the code. That's all the curly braces. You guys understand? So, you know. Put the curly braces in here, right? So normally it would like jump down to here, right? Like after the if else finishes, these are returned, so they're not going to, but normally it would jump down to here. So you would execute a block of code, then when it finishes, it would leap. It would have a go-to statement. It would have a branch. The branch would jump to here. But for now, we'll just make it easy on you. To return 1, remember that's just move R01 and then a BXLR. Okay, so I'm going to pause the stream now and give you guys 10 minutes to write this. Okay. It's too quiet on Discord chat, so I'm just going to pause, let you guys write this code, and then we'll come back and see how you did. Okay, 11. Let's do it that way. 11 minutes. Go. 1 1 1 1 1 1. All right, and we're back. So, anyone want to post their screenshots of the branching? Turn off my alarm. Anyone? We got 20 people in this class. Oh. Somebody screenshot your code. Post it. All right, we'll just start going to random students' code then. Sorry about that. Post a screenshot with your code in it. All right, x equals 30, y equals 20, z equals 10, or maybe you name them the other way. Okay, comparing x, I think these numbers are backwards, aren't they? It was like 10, 20, 30. Either. So compare R1 and R0. If x is less than y, then you branch to L1. Oh, I see. So you're doing it. I see. So you return. Nope. That's backwards. Yeah. So if x is less than y, you branch to L1, and then you return 1 and quit. So that's wrong, because if x is less than y, it's supposed to then compare x with z, right? This code is comparing x and y, and then immediately returning 1 and finishing. So that's not quite right. Then compare x with z. If it's less than, it jumps to L2 and moves 2 and returns. Yeah. So what you should do is say if it's greater than or equal to, jump to, you know, the else statement, right? All right. So let's see here. We got some other code. Let's see just what's on the screen. Interesting color scheme here. All right. So move, okay, x, y, z. Compare x1 and L2, or R1 and R2, x and y. If x is less than y, it jumps to L1. It then compares x and z. If it's less than, it jumps to L3, returns 1. Otherwise, it jumps here and returns 2. And then it's greater than, it jumps to L2, returns 3. Yeah, that looks good to me. And then at the end of it all, it comes down here and returns. Good. Yeah, this is correct. Very good. All right. So let's take a look at the other ones, but yeah, that's a general idea. Okay. So, here's if and else if. BLT does not have to be on the top. No, you do not have to have a bacon, lettuce, and tomato sandwich on top. You do them in any order you want. So in that case, I would structure it by putting the first branch to just jump down to the else statement as the first one. But you know, there's one of the fun things about assembly is like after you get it done, like kind of trying to clean it up and minimize the lines of code and stuff like that. You can oftentimes get some pretty good speed improvements by like tweaking it and reordering your stuff. Okay, so here we've got x is 32, y is 20. If x is greater than y, return 68, otherwise return -10. And you can do negative numbers, by the way. It's not going to show up in the operating system because it clamps to 0 to 255, but you can do negative numbers in assembly. That is fine. So we're putting 32 into R1. This time I'm calling R1 x. Ooh, that should be y here, not x. Y, there we go. Okay, so we're going to compare R1 and R2. And, yeah, it's, right. So this is the other way that you can do conditionals. So branches are not the only commands that you could put a GT or a LT or whatever after. Literally, almost any command in ARM, you can actually put a suffix in here. So this is saying move if less than or equal to. So if x is less than or equal to y, it will put -10 into R0. And if we want to make it a little more clear what's going on here, move if greater than or equal to, greater than. So if x is greater than y, put 68 into R0. If x is less than or equal to y, put -10 into R0. You guys see that? So this is the alternate way of doing conditionals using suffixes. Okay. So do you guys see this? You don't need a branch. It's nice. Because branches end up causing your code to like jump over here and jump over here and stuff like that. If you got like little one-liner if statements and things like that, it's usually better to just use suffixes, right? And so you just do this if you wanted. So you put 68 into R0, and then if it's less than or equal to, if x is less than or equal to y, then we put -10 into there instead. We could do it either way. The logic works out the same. So it just kind of depends, and the speed's the same, I think. So these two options here are both identical. Okay. Do you guys understand this? So the suffix method is actually really powerful. You can do things like say add if greater than R0, 1, right? And you can do this multiple times because remember, as long as you don't do another comparison, the secret comparison register is never changed, and so you can keep using the results of this comparison over and over again, suffix, 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 until you do another comparison. And so you can have, you know, if x is greater than y, add 3 to it. If x is equal to y, we're going to multiply it by. We're gonna set R2 R0 equal to R2 squared, I guess. I don't know. And if it's less than y, then we will subtract. I don't know. You guys see that? See, you can actually have multiple. So it's like you've got 3 lines in the first branch here. If x is greater than y, you got 3 lines in the second branch. If x is equal to y, you got 3 lines in the next branch if x is less than y. And as long as you don't do another comparison, it actually works out pretty well. Performance-wise, this isn't going to be good because it's going to run all 9 commands every time. And so at a certain point, branching is going to be faster. There's dead silence on the Discord chat. Do you guys see what's happening here? So this code here is like if x is greater than y, x plus equals 3, else if x equals y, these are kind of redundant, so we'll get rid of those. X is equal to y, x is equal to y squared, else x minus equals 3. Yeah, something like that. And we can clean this up a little bit. It's fine too. Yep. So every command can take a suffix. Almost every command can take a suffix. And so what this is doing, it's saying multiply if the result of the comparison was equals. Remember how there is branch if equals? It's actually branch with the equals suffix on it. Okay, so suffixes are used for conditionals. And so branch if less than, branch if greater than. But it's not just branches that work that way. You can also do add if greater than. Multiply if the result was equal. Subtract if x was less than or equal to. That should be less than. Thank you. Okay. So it saves some lines of assembly. It can make reading your program easier, but it can be a big speed increase, right? Because like it's actually slow to jump to a section of code, run one line, and then jump back. Like, that's needlessly wasteful. Whereas if you do something like this, sure, you're always going to run both branches, essentially, because that's going to cost you 2 cycles. But that's actually cheaper than having a comparison, 2 branches, and each of the branches jumps to a spot, runs code, and jumps back. Especially since branching can actually take about 8 cycles, depending on a lecture that you haven't had yet. But if you want to think of a branch as having an 8-cycle cost, that's kind of a good way of conceptualizing it in your head. It might not. It really depends on, again, that lecture that you haven't had yet. But if you want to think of a branch, every time a B appears, you can think of it as like an 8-cycle cost, an 8 instruction cost. Remember, a cycle is when the clock goes high and the clock goes low on a CPU. And in that time, when it goes high, it goes low, it will, in general, run a command. It'll run move R132. And the next time the clock goes high, the clock goes low, it runs the second command. Clock goes high, clock goes low, it runs the third command. So the clock rate of your CPU on the new Raspberry Pi 400, it gets 1.8 gigahertz. That means 1.8 billion times per second. The clock goes high, the clock goes low, and it runs a command. Now, if you have multiple cores, they're all running in concert with each other and stuff like that. And there's more computer architecture stuff that we'll learn later in the semester. But in general, that's a nice simplified way of thinking about the running time of your program. Clock goes high, clock goes low, it runs this, right? And so with a comparison, clock goes high, clock goes low, the thing are now compared, and the secret register has the results of the comparison in there. If you have one of these things, clock goes high, clock goes low, it'll run it, and if the result wasn't greater than, it just discards the result. 1 second. Spam, love it. Thank you. Okay, so this would always cost 3 cycles, no matter what. Okay, clock goes high, clock goes low. If it wasn't greater than, it just discards the result. Let's say it was equals. Then it goes high, goes low. This might actually have a 4 cycle cost. Like pretty much every instruction in assembly has a cost of 1 cycle. Multiply has a cost of up to 4, and branches have a cost of up to 8. And that's kind of oversimplified, but it kind of works if you just want to like have that schema in your head. And so if you weren't going to do it this way, if you're going to do this with branches, like this, the total running time of this code would be 1, 2, 3, 4, 12, right? This is a branch. And then, let's see, it jumps to here. There's different branches with different costs, but 13, 21, 22, 23. Now this code here, this is bad, right? Because his code sets 3 into R0 and then it falls through to here, right? So this code here is going to set 3 into R0, then it should return. It should have a BXLR right here. And same thing here. It puts 2 into register 0, it should return, right? And that code should return also, which it does. But this code, it'll put 2 into R0, and then it just goes on to the next line. Remember, in assembly, there's no curly braces, there's no flow control. It simply just starts at the top and goes to the bottom. And so if you work through the logic and it puts 2 into R0, what's the next line to run? Put 1 into R0. So that 2 just got overwritten. And then it returns. So, yeah, these labels don't stop code. It's just, it doesn't stop execution. It's a way of just like, being like, hi, I'm Bob, right? Like it just is a label for a line of code. It doesn't stop code from flowing down into it. And then you could jump to Bob at any time. It's just a way of labeling a line so that you could go to it, So if you do a branch, you could branch to Bob. Compare R1 and R2, branch if less than Bob, right? It jumps to it. If X is less than Y, it jumps to Bob. You guys understand? Starting to? Good. Let's talk about loops. So a loop is very similar to a conditional, except jump back up to the top, right? I mean, if you think about it in C++, right? Like, what's the difference between like while x is less than 10 and if x is less than 10? Like, what's the difference between these 2 lines of code? They look very similar, right? What's the only difference? While is a loop, yeah, but well, while is a conditional also, right? Like if x is greater than 10, it'll skip over the curly braces, right? So while x is less than 10, and we're always checking x minus 10 consistently with while. Now only at the top of the loop. Like if I did this, x is equal to 100, x is equal to 5. This is an infinite loop, right? You understand? It doesn't check x constantly. It's at the top of the loop. It says, hey, is x less than 10? 0 is less than 10. Yes. Okay. Sets x to 100, sets x to 5. When you get to the bottom, that's where the difference, yeah, very good, McCowan. That's the difference between a while and an if. When you get to the bottom of the while loop jumps back up to the top, and it does it again. It does the conditional again and everything again. With an if statement, when it gets to the bottom, it continues on. So this is go to top, or however you want to put it. Like that's the difference between a while loop and an if statement. All the rest of the code's the same. And when you see this in assembly, it's going to be almost identical, right? Almost identical. Okay, so here we've got code x equals 1, y equals 5. So it's going to compute 2 to the 5th power. Okay. All right. And assembly, it's the exact same thing. You just jump up to the top, you do the conditional again, and yeah. Yep. Okay. So we set x equal to 1. You notice I'm using like different registers every time. That's deliberate. I don't want you to think that like R0 is always X. You know what I mean? Like, it's just whatever. I could have picked R9 here. Like, just pick something. I just do that so I have a mental handle on register 4, register 5. Because otherwise, it could like, what's happening here? So I always tend to put the C++ code on the right hand side. I don't have a semicolon, I guess. It's a comment, so who cares? Okay. So that I can kind of keep track mentally of what's happening here. Okay. So, and since we're going to be multiplying by 2, remember multiply doesn't allow immediates. You can't have a hashtag 2 in a multiply. It's the weird exception to the rule. So if you want to do a multiply by 2, you have to put it into a register and then use that register in your multiply statement. Are there certain registers you can't use? Yeah, just don't use 13, 14, and 15. 15 is the program counter. The program counter is register 15 holds the address of the next line of code to run. And so if you set register 15 to 0, it'll segfault, right? If you ever try setting R15 directly, like set register 15 to 42, just try it. Like move register 15 5, it'll segfault your code because it tries running whatever's at memory address 5 next, and it explodes. So never write directly into register 15. Register 14. I'll put this down for you. Register 15 is the same thing as the program counter, which is the memory address of the next line of code to run. When you do a branch statement, it sets this for you. Okay, so you don't set it yourself directly ever. Like you do a branch to Bob, and then Bob is like over there, and so it figures out the memory address of Bob, and then it puts that into register. You don't have to worry about it. You just call branch, right? That's the proper thing. Register 14 is also known as link register, which is also known as the memory address we came from to this function. So it's the return address. So you usually end a function with bxlr, which is register 14, or pop that. And you start a program by pushing the link register onto the stack, and then you finish by popping the link register into the program counter, and then that returns back to the calling function. Do functions in a second. Okay, so if you see R15 on the screen, yeah, you shouldn't be writing it ever, unless you want to just like crash your code. Sure. Let's crash the code. Let's do this. G++, 8, run it, segfault. There you go. Curiosity satisfied. So our code is generating 2 to the 5th power, which is 32. 2, 4, 8, 16, 32. Okay. Why didn't they make R15 read-only? Because you can write to it, like this. Like this is writing to the program counter. You're writing to the program counter, but what address is it? It's whatever address was in register 14. So you're another way of doing this would be move register 14, register 15. Or, sorry, register 15, register 14. And so that's another way you can return from a function, as long as our 15 and 14 have, like as long as you haven't called another function, let's put it that way. Then you can move register 14 into register 15, and that would return from the function. Don't do that, though. Don't do that. So you BXLR or this. These are the two proper ways of doing it. Okay. Yeah, we're going to over that. We're going to go over pushing and popping next, Shab. Okay. So here is our loop. So you can see it's not a whole lot of code. This is the bottom of the screen here. So we're doing a for loop, right? So for int I equals 0, I is less than 5, I plus plus. Every time we do it, double x. X starts at 1. Okay. So what I'm doing is y is 5. Okay. So I'm doing a subtract and set. So subtract and set. You know how I said there are two different ways of doing compare? S suffix is the same thing as compare, in this case, register 5 with 0 after the sub runs. Okay, so if you do subtract and set, what this does is it subtracts 1 from R5, and then it does a free, no cycle cost, comparison with 0. Okay, so you don't need to put a CMP into your code when you're doing something like this. If comparisons with 0 are useful for you, then the set suffix might be for you. You could, rather than doing this, we could say CMP R5 0. This would be the exact same code. Okay, so we start with R5 at 5. And then we run through the loop, we subtract 1 off the top, we compare it with 0. If it's less than 0, we're done. Otherwise, we multiply x by 2, we go up to the top, subtract 1, it's now 3. Is it less than 0? Nope, multiply x by 2 again, subtract 1. Is it less than 0? Nope, multiply x by 2, subtract 1. Is it less than 0? Nope, multiply x by 2, subtract 1. Is it less than 0? Nope, it's still 0. 0 is not less than 0. Multiply x by 2. Subtract 1, we're at -1. -1 is less than 0, and so it goes to done and quits. Okay, so that is a for loop. Okay, but let's do it. We usually count down our for loops with y minus minus rather than I plus plus or something like that. Okay, so if you're doing a for loop up to 5, rather than adding 1 to a loop counter every time, typically we will count, unless we need y again, we'll decrement it by 1 every time. That way you don't need to use another register. Right? Notice how there's no I anywhere in there. There's no I variable. Right? Do you see that? Like I got an x, I got a y, and I got a times 2. There's no I. I didn't need to make one. The reason for that is because if we just decrement y each time, when we hit 0, we finish. Okay? So it saves you register. Yeah, it's a very common optimization. And the other nice thing about it is that we can we can do this instead. Subtract and set R5 1, same as the 2 lines above. Okay. Option 1. Better option 2. So this line of code here, subtract and set, it does the subtraction, then it does a free comparison with 0. That's another reason why we count down, because 0 is a magic number. When you hit 0, you're done. It's like you're using a while loop more likely than a for loop. Yeah, well, we don't, for loops and while loops are kind of the same thing, right? You know, this depends how much you're doing in the parentheses, I guess. I don't know. So, yeah, so this was rewritten not to count an integer up to 5 and compare against 5, but rather to count down from 5 to 0. It's a very common optimization technique in assembly. And so you only need one line of code, right? One line of code to do the countdown and the comparison, one line to do the terminate, and then the rest of it is the body of the function. Body of the loop, I should say. The bottom of a loop is to just jump back up to the top. So this is what makes it a loop instead of a conditional. At the very bottom of a loop, you just jump back up to the top. So I make a label here called top, jumps back up to the top. Now you get into trouble when you got two for loops, because then, you know, if you call them both top, it's like when you have a vector. The first one's vec, and the second one you're like, oh man, it's got to be vec2, but that means the first one has to be vec1. Ah, dang it! Now I got to go back and change vec to be vec1, and so if you have multiple for loops, you got top, then it becomes top 1, top 2. I don't know, or you just use label 0, label 1 like the compiler does. It doesn't really matter to me. You just gotta have it. Every label has to be unique. You cannot have the same label twice. Same source code. Top 2, top 3. Yeah. Loop, top loop. I don't know. Top 1, top 2. Yeah. What does the S suffix mean in general? The S suffix means you do a comparison with the target register. The S suffix means do a free comparison between the destination register and 0 after the command runs. Okay, so in this case, the destination register is R5. We're subtracting 1 from it, writing the result into it. After we write the result into it, we do a comparison with 0. And so these two lines of code here are exactly the same as this. And you can add the S suffix to pretty much everything as well. You do a move and set, move S, and that'll check to see if the thing you put in there was 0 or not, or greater than 0, less than 0, equal to 0. Okay. So, yeah. So that's variables, conditionals, loops. Loops are almost identical to conditionals, except at the very bottom, you just jump back up to the top. That's it. So I'll give you guys another 10 minutes to work on your code. This time I want you to write a for loop that 10 times prints hello world. No, you don't know how to print hello world. Let me show you how to print hello world. So I've got here a function called print hello. It's in C, doesn't really matter. And so if I want to call this function from assembly, no, that's our next topic. Nah, all right. So just stick with this for now. We haven't done functions yet. So write a for loop that will add up all the numbers from 1 to 10. How about that? Or add up the numbers from 0 to 9. Make it easier on you. Find prime numbers, zeta function. Okay, so lab time, write a loop to add up all the numbers from 0 to 9 or whatever. Okay, so we'll come back at 11:56. Okay, and I will leave the source code here on the screen, and I would just use option 2 if you want. And then at the bottom, make sure you put the result into register 0 before you return. You can check your result by echoing see the result with echo. Okay, and then you can see if your code's correct. All right, 11:56. See that. So like, yeah, the BAL top should just be eliminated, because this isn't like two different programs or anything like that. There's no curly braces or anything like that in assembly. If you didn't have the BAL top there, it would do the move 1, R1, move R2, and then it would just simply continue on down into here. So things just fall through in assembly, and that could be lethal sometimes, because in cases like this, I guess in this case it doesn't matter, because it's just going to jump to the next line, which it would do anyway. But like if you forget to like return like at the bottom of the code, then it just goes off into la la land, right? And it you know, it's gonna seg fault, you know, if you don't have anything at the bottom of your code, because assembly just starts at the top and it just runs one line of assembly to the bottom, right? Can you make this shortcut file public? What is this shortcut file? Mulek. This is multiply if equals. Yeah, I'll send out the updated demos in a second. Yeah, they're all sent out. They're in a directory you have called ASM demos, but the updates I'll send out in a second. When is the first assembly assignment? I guess I'll push that out. It'll be called ASM first or whatever. So keep an eye on that in just 1 second. All right, so then otherwise we add R2 and R1. That's going to add R1 to R2, so that's going to add 9. Subtract 1. Yeah, you can eliminate that middle one there if you wanted. It doesn't matter. So that's going to take it down to 8. Branch of less than to done. Otherwise, branch to the top. Yeah, so you should probably check to see if there's an off by 1 error in that. Okay, so for your first assignment at assembly, there we go. Wow, that was a slow load. You are going to implement a few different algebraic functions. 4 times x, a multiply and a square, some algebra, and then it's a code golf assignment. So if you guys have never done code golf before, the notion is trying to minimize the code that you write. And so when you write your code, the first thing to do is to make sure it's correct, and you're going to type make to build it, out to run it, input tester to test the correctness of it. And then once you've gotten it correct, then you're going to try optimizing the code. And the way that you're going to be scored is that every normal command, an add, subtract, a move, is 1 stroke, a multiply is 4, a function call, which I guess we'll go over on Thursday, is 40. and the top 25% of students will get 25% added to their grade. So lots of extra credit available for the top 5 students or whatever in the class. And so you're trying to get your stroke count down as much as possible. Okay. How do you get a hole in one? I don't think you can. I don't think you can do this in one stroke. It seems unlikely to me. I guess you could branch into a C++ program that does it for you, but that's against the rules. That's not allowed. Okay. Okay. So let's see here. Add R1 to R0. So that's going to add 10 into it, and then subtract. I think these two need to be in the opposite order. So you're supposed to add 0 to 9, not 1 to 10, right? So branch should be less than or equal to done. Yeah, that's fine. Okay. Yeah, so these two are in the opposite order. That's the only problem I see with that. Okay, so take a look on the server for the ASM first folder and get going on that. There are some helper functions in here, but basically the main in this is actually going to be in C++, and the C++ code is going to call your code. So you're going to write a few different functions, foo, bar, baz, whatever, and your goal is to minimize the stroke count as much as possible. Okay, so we'll talk more about functions on Thursdays, but it's out there, so you can start working on it now if you want. Okay, so thanks everybody. Stay healthy, and I will try to as well. I'll let you know when I get my COVID test back, when we can go back in person. But for now, I have to stay at home. Okay, so see you guys on Thursday.